Welcome. The use of weather radar has greatly improved overall safety. Understanding the technology behind its applications is essential when it comes to safely navigating the skies.
Did you know that a recent study indicates over 53% of us pilots have faced instances of radar mismanagement due to lack of understanding or lack of training?
The following questions will help us improve our knowledge and understanding and change those statistics dramatically.
The first question we have to ask ourselves is, what exactly are the characteristics of the weather radar beam?
The weather radar beam, as you know, is cone-shaped, which means it spreads out as it travels. This is similar to a flashlight beam.
For our next question, we are taking a look at what altitude range we generally find the most intense weather inside a mature cumulonimbus cloud.
Generally speaking, this would be between 10,000 and 25,000 feet.
Now we know what we want to scan. The question is, how do we tilt our beam? But what exactly is the beam tilt angle reference to?
It's important to understand that the tilt angle on your weather radar is relative to the horizon, not the pitch or flight path angle.
Knowing all this, on a manual tilt weather radar, for the pilot flying, what is a proper tilt and range setting before taking off?
For a manual tilt weather radar, a good starting point is a tilt angle of 4 degrees and a range of 14 nautical miles. Why 4 degrees? Well, at 40 nautical miles, this tilt will put the center of your radar beam right around 16,000 feet. That's a sweet spot for seeing the heart of a thunderstorm nearby and assess the intensity of the whole cloud.
So then, using the same manual tilt during our descent and approach, how should we manage our tilt?
The key here is to adjust the tilt angle gradually. As you're descending, start by tilting your radar beam downward to get a good look at the weather below you. Then, as you get closer to your destination, generally speaking below 20,000 feet, start tilting the beam upward. This will help you scan for the region of highest intensity within the cloud, giving you a heads up about any severe weather.
Now for a very practical question, how can we determine the height of precipitation based on tilt angle and distance?
Step number 1, define the tilt angle and subtract half the beam width. In commercial jets, the beam width is around 3 degrees, so subtract 1.5 degrees. Step number 2, determine the distance to the storm and multiply that result by 100. You now got the height of the precipitation relative to the aircraft's altitude.
For our next question, suppose we are flying at flight level 250. Our tilt is set manually at -1 degree. Beyond what range do we expect to see ground returns?
Well, let's use the formula. Height equates to the tilt minus half of the beam's width times distance times 100. Plugging in the numbers, 25,000 equates to the distance times -1 minus 1.5 times 100. Solving for distance, this equates to 25,000 divided by -250. Therefore, the distance equates to -100, or 100 miles from the aircraft's position.
As we keep tilting upwards, beyond an altitude at which there are no longer radar returns, what does this imply exactly?
When all returns faded away, you've determined the top of the precipitation. But remember, the top of the cloud and the turbulence bow may well extend above that.
What is the correct description of the displayed tilt angle value on our navigation display?
When you see the tilt angle displayed, it's actually showing you an average of the lower beam and the higher beam. It's a middle ground that gives you a general idea of the beam's direction.
Oh, and maybe you have noticed that during cruise, some radar returns disappear as we get closer. The question is, why is that so?
Well, the culprit here is often the lower edge of your radar beam. This is especially relevant with radars using only a single beam. So, even though the storm might be there, the radar beam is looking too high to catch it.
Here is another question for you. You might wonder, but on the multiscan weather radar, when manual tilt is selected, what exactly is the value of the tilt angle, or how does it differ from the auto tilt mode?
When you switch to manual tilt mode, there's just one beam doing the work. So the tilt angle you see on the display is the tilt of that single beam, plain and simple.
We have seen that it is possible to overscan some of the weather. But what would be the risk of underscanning weather?
Basically, it means your radar beam is aimed too low. So you might be missing out on some important weather information that's happening in front of you.
Now more of a basic question for those new on type: what is controlled by the gain of the weather radar? And, for those of you more experienced pilots, how is the gain scale setting interpreted?
It's like a volume knob for your radar. The higher the gain, the more sensitive your radar is to weak echoes. So, if you're struggling to see some distant storms, try turning up the gain to boost those signals. The gain knob allows you to modulate the gain from -16 dBz towards +10 dBz. So generally speaking, full-scale deflection will gain you one color. For reference, the colors you see are: for black, anything below 20 dBz. For green, as from 20 dBz. For yellow, as from 30 dBz. And for red, from 40 dBz.
Time for a mini quiz. Can you guess which statement related to the weather radar is false?
So it is true to say that turbulence, indicated by the magenta color, is not affected by gain, and that the black color indicates any precipitation below the 20 dBz threshold or no precipitation at all. The gain modulation, depending on the model, will modulate from -14 dBz to +14 dBz, or a little over one full color difference. The gain will not have a pronounced effect on ground returns.
Oh! The flight has inadvertently entered some bad weather. How can the pilots mitigate and provide the passengers and crew with the safest course through the weather?
If ever you would find yourself in inadvertent weather, try decreasing the gain on your weather radar. This will help you pinpoint the areas with the strongest echoes, which are likely the most dangerous parts of the storm.
Did you know that when it comes to interpreting the weather radar, it is more about shape than it is about color? From the following examples, which one could be considered the least risky?
A large green area on your weather radar with few scattered yellow and red specks usually means there's a nimbostratus cloud hanging around. These clouds are like the steady rainmakers. They're not as dramatic as thunderstorms and can generally be considered safe to traverse.
Something you and I better be aware of when navigating the weather is called attenuation. Do you know what is meant by that?
It's important to note that areas of heavy precipitation may appear black behind a red area on the radar display. This can sometimes be misinterpreted as a safe region, but the opposite may be true. Attenuation can thus mask areas of severe weather and should be considered as such.
And now for our more advanced weather radar, the RDR 4000. Are you aware of its different functions? And can you guess what is missing on its operating panel?
The RDR 4000 does not have a tilt function. It is replaced by the elevation function instead. Instead of scanning the weather along a slope, controlled through a conventional tilt knob, you will see the weather reflected as an altitude slice at the selected elevation, controlled through the elevation knob.
Now, as for an important definition, to understand the operational use of the RDR 4000, what does on-path weather mean to you?
Only on-path weather is shown because the off-path weather is suppressed. Observe from the picture that in cruise, for the older software, only the weather above 25,000 feet is indicated on the radar display.
Some specific shapes may appear using the RDR 4000 that we need to understand. For example, during cruise, how would you assess a green full color over and inside of a red shaded return?
A green full color over and inside of a red shaded return may be indicative of a convective core, off-path, or below flight level 250, with its less reflective, yet potentially still convective area, above flight level 250, or on-path.
During takeoff and during approach, below 10,000 feet, on the RDR 4000 WX radar, what is the significance of those shaded weather returns?
The shaded areas indicate radar returns above 10,000 feet.
Now during cruise, on the RDR 4000, what do these same shaded areas tell to you?
In cruise, we find the inverse logic, meaning the off-path weather is now below.
Okay, moving on to some movements in the skies. Did you know that there is a limitation as to which distance the radar can accurately detect and display turbulence? Any idea?
The magenta returns indicative of turbulence are only displayed up to 40 nautical miles, or 60 nautical miles in the newer models.
Moving on to a super simple basic question. You are in cruise phase. Heading north. You observe significant radar returns intersecting the flight path straight ahead. Suppose the wind is blowing from heading 270/50. What direction will you deviate to?
With the heading towards the north and the wind blowing from the west, the weather system will cross the flight path from left to right, meaning the deviation need to be taken to the left, upwind of the system.
Now, your attention please as we are heading towards a cluster of cumulonimbus clouds. In general, when would you decide to circumnavigate a whole system of weather?
Whenever the convective reflections cover more than 6 out of 8 of the skies, it is recommended to avoid the whole weather system.
Does size really matter? How would you assess the risk when during cruise you see a small green radar return moving towards you?
Even a small green return at cruise altitude is most likely to be hazardous, as it is indicative of an isolated convective cloud top consisting of ice crystals. Use the manual tilt downward momentarily to understand the intensity at lower, more reflective areas.
We are clear of the cluster, yet we need to remain vigilant. To provide us as a crew with optimum awareness to determine strategy and make reactive decisions, what would be an appropriate range setting on the navigation display for both pilot flying and pilot monitoring?
To avoid the blind alley effect that could occur if both pilots have shorter ranges selected, make use of both navigation displays. In cruise, the pilot flying is recommended to have the range set at 80 nautical miles. That allows for a proper assessment of the intensity of the weather ahead, and a good time to decide on any required deviation. The pilot monitoring's display should be at 160 nautical miles, a good range for long-range tactical awareness.
Wow, surprisingly, some weather returns suddenly appeared out of nowhere at close range. I wonder why could this be?
This is because the black returns at further range may yet be below the threshold of 20 dBz. As the weather comes closer, due to the increased reflectivity at shorter range, the weather is now picked up and displays green. To avoid surprises, increase the gain to pick up those hidden returns and assess if avoidance is required or not.
When it comes to scanning weather, the acronym VAST may help us to stay ahead. But what does VAST stand for?
A good scanning technique is achieved by first of all assessing the shape of the cloud visually or by looking at the radar image. Secondly, being aware of attenuation. Next, understanding the use of the gain to adjust for sensitivity as required. Finally, of course, the correct use of radar tilt as explained before.
After making a VAST scan, what margin would you need to safely overfly a cumulonimbus cloud?
If there is no other option available, make sure to have at least 5,000 feet clearance above the cloud tops, provided these are not growing at considerable rate.
Always remember, though, the risks involved when it comes to overflying weather. What would you need to be aware of?
When considering how to deviate weather, keep in mind that the cells may be growing vertically and expanding horizontally. Understand the direction and the speed of the cloud or the weather system, and beware of the turbulence bow that may extend well above the cloud. Beware that the radar can only detect precipitation.
Most of the times, it is best to simply avoid left or right. By what distance would you make such avoiding requests and why?
In cruise, it is recommended to make such decisions by 80 nautical miles, leaving enough time to coordinate with air traffic control and minimize the off-track distance. Remember that at Mach 0.8, you are cruising at about 8 nautical miles per minute, meaning only 10 minutes away from the weather.
As we are approaching our destination, it gets very busy. Air traffic control sends up refusing us a much-needed heading deviation. In such a case, what are the options left?
Keep in mind a contingency maneuver as air traffic control may be saturated with traffic avoiding at the same time. In such a case, consider asking for a heading change, a level change, entering a hold, or if no other option remains, executing the deviation declaring a mayday.
Proper preparation prevents poor performance. Websites such as windy.com provide us with additional layers of useful and practical information. One of these layers is the clear air turbulence layer that is expressed in EDR. But how to make sense of these values?
One of the layers provides info about the eddy dissipation rate, a value indicative of clear air turbulence that is impossible to detect by weather radar. To improve our awareness, let us take a look at the values provided. For a medium-sized airplane such as the Airbus 320, whenever the EDR values exceed 20, there is probable moderate turbulence present. When the values exceed 44, severe turbulence is present, and a deviation or a level change might be required. In any case, avoid those areas that have values present over 79 that indicate extreme turbulence.
Another such layer is called the CAPE layer. Let us dive a bit deeper into this layer of information.
The CAPE layer refers to the presence of convective available potential energy within a specific atmospheric layer. This is the stored energy in the atmosphere due to temperature differences between air parcels at different altitudes. The higher the values, the greater the instability in the atmosphere and the stronger the potential for thunderstorm development. While this layer is a useful tool for identifying areas with potential for thunderstorms, it's not the only factor to consider. Other factors like wind shear and moisture also play a role.
Another very practical skill is the ability to quickly determine the cost in terms of fuel it would take to circumnavigate weather. Imagine, for example, that you would need 80 nautical miles weather deviation. How much fuel we would need to realize that deviation?
At Mach point 8, the airplane is moving at approximately 8 nautical miles per minute. Consequentially, the time needed to deviate, say, 80 nautical miles would be 10 minutes. Next, open the fuel page to determine the fuel flow per minute. For the Airbus 320, this is around 40 kilograms per minute and 50 kilograms per minute for the Airbus 321. So for an 80 nautical miles detour, the extra fuel would be around 400 to 500 kilograms.